Have you ever looked at your own shadow and thought, hey, that's geometry? Yeah, probably not. But it turns out that simple shadow you cast on the ground is the key to some really powerful rules in geometry, rules that have been around for thousands of years. So let's dive in and see what's going on here. So yeah, this is the big question, right? What in the world do shadows have to do with geometry? Well, stick with me because by the end of this, you're not only going to get the answer, but you'll see how this one simple idea lets us solve some pretty tough triangle problems, all thanks to a little something from the master himself, Euclid. Okay, first things first, we have to get our heads around this one core idea, projection. So in the world of geometry, a projection is basically a perfect shadow. Imagine the sun is directly over your head at a perfect 90-degree angle, so your shadow drops straight down. That's a projection. And here's the more, textbook definition. The perpendicular projection of a point is just where that point would land if you dropped it straight down onto a line. Think about it like this. You're holding a tiny pebble right over a line drawn on the floor. You let it go. The spot where it hits, yep, that's the projection. So this really only plays out in two ways, and they're both super simple. If your point, let's call it A, is floating above the line, its projection, which we'll call A prime, drops right onto that line. But what if point A is already on the line to begin with? Well, then it's its own shadow. It doesn't go anywhere. Its projection is just itself. That's it. All right, so we've got single points down, no problem. But what happens when you want to project something bigger, like a whole line segment? Well, the cool thing is it builds right on top of what we just learned. And the rule here is actually really, really easy. To find the shadow of a whole line segment, you don't have to worry about all the little points in the middle. Nope. You just find the projection of the two endpoints, A and B. You find their shadows, A prime and B prime, and then you just connect the dots. That's your new line segment, the projection. Now, this is what you're going to see most of the time. If you have a line segment that's tilted at an angle, its projection is going to be shorter than the real thing. It's just like when a ladder is leaning against a wall. Its shadow on the ground is always shorter than the actual ladder, right? Same idea. But what if that line segment is standing perfectly straight up, completely perpendicular to the line? Well, in that case, both endpoints, A and B, they project down to the exact same spot. So the shadow shrinks from a line all the way down to a single point. Poof, it's just a dot. And that brings us to our last case. What if the line segment is perfectly parallel to the line? Just floating flat right above it? Well, that's the one time its shadow, its projection, is the exact same length as the original. This is the only time the projection isn't shorter. So all of this leads us to one huge, super important rule about the length of these projections. It's something you can absolutely count on every single time. And here it is, the big takeaway. The projection is never longer than the actual object. I mean, think about it. It just makes sense, right? A shadow can be shorter. It can be the same size in that one special case, but there's no way it can ever be longer than the thing that's casting it. That's physically and geometrically impossible. And here's how the mathematicians write that same idea down. The length of the projection is less than or equal to the length of the line segment itself. That little less than or equal to symbol perfectly covers all the situations we just saw. It's shorter if it's slanted and equal if it's parallel. Okay, so we've got projections down. Now it's time to unleash the power tool. We're going to see how this idea of shadows helps us use one of the most famous theorems in all of geometry, Euclid's theorem. This is where it all comes together. Now, Euclid's theorem has a very specific playground. It only works with a right-angled triangle. And not just any right-angled triangle, you have to do one more thing. You have to drop a line, called an altitude, from that 90-degree corner straight down to the longest side, the hypotenuse. See how that line splits the hypotenuse into two smaller pieces? Hey, wait a second. Those are the projections we've been talking about. And this is where the magic happens. Euclid gave us these incredible formulas that connect all the pieces. So look at the first one. It says that the square of the side AB is equal to its projection BD times the entire hypotenuse BC. The exact same idea works for the other side, AC. And that third formula? That one connects the altitude itself to the two little projection pieces. It's just so elegant. Okay, the theory is cool and all, but let's get our hands dirty and see how this thing actually works. We're going to take a problem and use these formulas to solve it, step by step. All right, here's our setup. We have a triangle. It's right-angled at B. We've dropped that altitude, BD, down to the hypotenuse. Now, we're told that the two pieces of the hypotenuse, those projections, are 9 centimeters and 16 centimeters long. Our job? Find the lengths of the other three lines, AB, BC, and that altitude, BD. So here's our game plan. It's pretty straightforward. First, let's just find the length of the whole hypotenuse. That's easy. It's just 9 plus 16. After that, we just apply Euclid's formulas, one by one, to find the square of each side we're looking for. Then, we just take the square root, and we'll have our answers. Let's do it. First up, side AB. So our formula says that AB squared equals its projection, which is that 9 centimeter part, times the whole hypotenuse, which we know is 25. So, what's 9 times 25? It's 225. Take the square root of that, and you get 15. Bam! Side AB is 15 centimeters. One down. All right, next up is side BC. We're going to use the exact same logic. BC squared is equal to its projection, which is the 16 centimeter piece, times that whole 25 centimeter hypotenuse. Okay, so 16 times 25 is 400. And the square root of 400, that's a nice round 20. So our second side, BC, is 20 centimeters long. And for the grand finale, let's find that altitude BD. For this, we use our third formula, which says its square is just the two projections multiplied together. So we multiply 9 by 16, that gives us 144. And the square root of 144 is 12. The altitude is 12 centimeters long. And just like that, the whole puzzle is solved. Pretty cool, huh? So we went all the way from simple shadows on the ground to solving a whole triangle. Now, it's your turn. Take a look at this figure right here. Based on everything we just talked about, what do you think the projection of the line segment AB would be on the line BC? Think about where that shadow would fall. It's that kind of thinking that takes a simple idea and turns it into a seriously powerful tool.